So in this lecture, we're going to start a discussion of a classic graph theory application called the traveling salesman problem. And to do that, we need to start by introducing a new concept called a weighted graph. Right? A weighted graph is just a regular graph, like the one on the left, but where each edge is assigned a numeric value called its weight, or sometimes its cost. These costs can be any value you're interested in. For example, it could be the cost of an airplane ticket between two cities, could be the latency between two routers, or the strength of a chemical bond. Now, the idea behind the traveling salesman problem is that you're a salesman and you travel between a set of cities in your region, and you need to plot an itinerary that has these requirements. Right? First, you have to pass through each vertex exactly once, and second, you have to start and end at the same city. So that's kind of an exception to the touches exactly once, right? Just like with all the other circuits we've looked at, the starting and ending point is the exception. So from the terminology we used in our previous lecture, what we're looking for here is a Hamiltonian circuit through the graph. But we're going to add one additional criterion. We want to find the circuit that has the lowest minimum cost. And this is what we call the traveling salesman problem. Now, for relatively simple graphs like the one on the previous page, yeah, okay, it's not too hard. You can kind of look at it, work through a couple of examples, and pretty quickly convince yourself that you found the cheapest path. With a more complicated graph like this one, you really can't do that. We need some kind of more formal algorithm or procedure for answering this question. And to do that, we have really two very basic requirements. Right? We require an exact solution for every possible graph that we could start with. And we require that our algorithm is going to finish in what I'm going to call a reasonable amount of time. If you go on from here, you're in a computer science program, you take a class in the analysis of algorithms. It's a required class for every computer science program. You'll go into much more detail about, first, what constitutes a reasonable time, and second, how you go about calculating those times for different algorithms. For now, I'm just going to say reasonable. It has to end, and it can't take weeks, right? So the problem here is that there is no known algorithm that satisfies both of these requirements. There's a brute force method where you're literally just trying everything, but the time required to do that blows up really quickly as the size of the graph increases. So, what do we do? Right? If you're the scheduler for a sales organization, you got to come up with something, right? You have to plot an itinerary for your salespeople. So, what we do is we come up with an alternative. We really can't relax the runs in a reasonable time requirement. Doesn't matter how good your algorithm is, if it can't give you an answer soon enough for it to be useful to you, then it's no good. So what we will do is we'll relax the first requirement and say we'll be satisfied if we can get a good solution, if we can get a solution that we know is at least close to that minimum, and we get it most of the time. Right? We get it from most graphs. So in the next lecture, we're going to start looking at two methods. One's called the nearest neighbor method. The other is called the best edge method that fit into those good enough categories. They give us answers that are, at the very least, close to the right result, and they give it to us for most of the graphs that we could potentially input. So link below will take you to the next lecture. And of course, if you like this presentation, please don't forget to click on the like button as well.